The next talk will be given by Yuan Liu, who will tell us about unification of finite symmetries in simulation of many-body systems on quantum computers.
How do I flip the slides? This one?
Yeah, sure.
Cool. Good. So I'm Yuan, so I'm from NC State. Today I'm going to share some recent work on thinking about leveraging symmetries in quantum simulation in general, and ideas on how possibilities of seeking new quantum advantages from a symmetry perspective. And so we know symmetries are really ubiquitous in quantum systems. So this ranges from lattice condensed matter systems, for example, translation symmetries or more general space groups, and to point groups in molecule systems for small molecules in quantum chemistry, or for more abstract sort of groups, for example, the symmetric groups that governs the fermionic or bosonic statistics. And it turns out that, not surprisingly, many properties can actually be inferred just by a symmetry argument without actually solving the problem. For example, in quantum chemistry or chemical physics, routinely people take lots of spectroscopy that's used as a signature to infer some information about dynamics or static properties of molecules. And turns out that all the distributions, lots of distributions, and the peak width and the intensity can be inferred from selection rules, for example, and degeneracies of lots of the energy levels in molecules. That's all a result of just a simple group theory and representation theory. And there's also a need to determine properties across different symmetry sectors. And I'll give you one example of this relevant to quantum chemistry in energy harvesting settings. So there's a process called singlet fission. So the idea is that if you give me two molecules to start, and they are in a singlet ground state, S0, S0, and I'm going to try to excite one of them to the first excited singlet state, and then turn that into S1. And turns out oftentimes the electron-electron correlation interaction between the two molecules will induce a two-electron process to arrange that singlet-singlet state to a triplet state on the two molecules. And turns out the triplet state have much higher lifetime than the singlet state. And then that longer lifetime plays an important role for this energy excitation in electronics to catalyze downstream chemical processes. And this is really important for photosynthesis process or artificial organic LED systems or energy harvesting and conversion systems in general. And so there's driven by these applications, there's a general need that we should think about a unified framework to do quantum simulation that can incorporate all sorts of different symmetries. And of course, this is not a new idea. So if you think about symmetries, right, we have in the mathematics, there's a whole field of group theory and representation theory. And even on classical computers, there are lots of classical quantum chemistry algorithms that's trying to kind of actually get all of this symmetries adapted state out. But oftentimes, the challenge is that for lots of the group, actually the classical computation cost is exponential. For example, in the case of a permutation group, to get all the correct singlet triplet spin coupling path, there are combinatorially many possible pathways to enumerate. As a result, it's really exponentially challenging to get all of this correct on a classical computer. And on a quantum computer, it's more powerful. So it turns out that indeed, we have more efficient routines, subroutines to leverage symmetries. For example, there's the Fourier transform that you can perform on general groups. And it's efficient actually for lots of the groups. And this is useful and can be served as subroutines for lots of other useful algorithms. For example, the generalized phase estimation and the short transform. Interestingly, all of these applications people find about leveraging symmetries mostly in quantum information setting, for example, testing symmetries of states or operators. And also, there's a recent work on port-based teleportation. So the sort of application or ideas how to use this in quantum simulations are really mostly unexplored. So in this work, we ask the following sort of two questions. One of them is that, can we actually leverage the coherent nature of quantum computers to prepare, let's say, a coherent superposition of all possible symmetry sectors simultaneously? And then that will allow us to actually have the coherent dynamics or simulation across all symmetry sectors to deal with the application problems I mentioned about. And then the second part is that if we can do that, can we actually now enable new possible pathways to think about different kind of quantum advantage that we can talk about in chemistry applications or in general quantum simulations. So the answer, of course, to these questions are yes. For the first question, it's a firm yes. So I will show you a much more reduced and efficient way circuit constructions that improve upon the group Fourier transform and generalize the phase estimation to do symmetry adapted simulation. And then for the second problem, the quantum advantage problem, I'm going to try to lay out possible directions, but I wouldn't say that we solve this problem. But I think it's a longer term and community effort to do it. So to see how this works, let me just start from a simple sort of mini task. Let's say I'm given initial state psi of a generic system, and my Hamiltonian system have a symmetry group G. And then I wanted to construct a projector P gamma to project that state to the gamma sector. And so group theory tells us, well, the way to do that is to find a sort of a giant linear combination of lots of representations, rho G, of each group element G, and then apply that unitary to my initial state, weighted by different coefficients, chi, gamma. That's the character of the group. And then I just perform a giant sum over all the group elements. And that's the LCU, so I can do that. Well, so if you think about this, right, so there's a quantum circuit naturally you can write down to do it, where you just do an ancilla state preparation. That's your LCU prep. And then in the middle, you do lots of controlled group actions. That's the sort of select stuff. And then you undo it. And then another name of this is really just the generalized phase estimation, right? So if you think about the typical phase estimation, you can view this as a special case of the generalized phase estimation over cyclic groups, where the symmetry you're dealing with is essentially the continuous time translation symmetry of your system. And then you are discretizing your time. And then that gives you the sort of conjugation of estimating energy from a different sort of a slice of T. Okay? So in this fashion, you know, we kind of have a better understanding of this algorithm. But this seems to work, right? But what's the point? The point is that this generalized phase estimation construction actually ignores some key properties of the group, especially for non-abelian group, where not all group elements are created equal. And there are some subset of group elements that shares very similar properties, and then they form a conjugacy class. So let me give you a simple example using the D4 group. So D4 group is the symmetry of this square, right? So it has two generators, A and B. So if you keep multiplying A, which is a rotation by 90 degrees, and then 4 times you're going to get back to yourself. And then there's the B. That's just the reflection. Okay? So this group, D4, has 8 group elements. So in principle, to do LCU, you have to do like 3 qubits, 8 times, right? But actually, if you kind of just to see how one group element can be related to the other after a conjugation of all the rest of the group elements, you will see that some of those are just forms cliques. And then in the end, this whole D4 group, you can show that it actually only have 5 conjugacy class instead of 8. So as a result, you can actually simplify all of this group Fourier transform into something more simple. We call it the quantum character transform, where you can ignore all the degeneracies within the conjugacy class and then only focus on the irrep label. And then this allows you to have reductions on qubit count. So this dihedral group seems to be trivial. You know, you save 8 to 5. But if you work out the qubit savings on symmetric group, you can show that it will save you the ancillary qubits from n to roughly square root of n. And then, so the circuit depth saving, we're still working on that for the symmetric group. But in principle, one can also show that there's a interesting sort of recursion that one can write down to get more interesting savings. And so if you compare this with a Fourier transform, right, you can see that you get both qubit count and possible circuit depth saving. So with that, we can now actually combine this quantum character transform with the LCU. Now we're just summing over the conjugacy class instead of the group elements. And then the conjugacy class, of course, you can now see that this will be controlled over the conjugacy class, which is much fewer ancillary qubits. And then each conjugacy class, now you sort of have to sum over what's happening in the conjugacy class. But now, because all the group elements are sort of equal within that conjugacy class, you just have to do a uniform superposition. And then this is sort of for continuous group, you can show that this reduction can be performed analytically. And you don't even have to use that ancillary qubit that many times. So if you have two groups that's commuting, then you can kind of just stack on top of this to give you sort of a two-group version of symmetry adapted transformation that allows you to project to label the state on the erapes of the two groups. And with that, you can combine this with any subroutines that you want to get a symmetry-adapted quantum simulation. For example, you can combine that with a quantum phase estimation. And this allows you to estimate the energy of your given state. But also, the energy will be labeled by the symmetries of that state. For example, is it triplet? Is it singlet? Is it this particular reflection symmetry or that? Right, so this gives you a sort of very interesting coherent simulation capabilities. I'm going to skip all of this condensed matter examples, and then just to highlight a little bit of quantum chemistry examples. It turns out that in the first quantization, this will allow you to simulate spinful quantum chemistry, where both the spin and orbital degrees of freedom are considered. And even in the spin-orbital coupling case, even there's spin mixtures, that's not a problem, can be dealt with in the same fashion. And then so symmetry adaptive circuit in the first quantization looks so simple because the permutation elements are really just the swaps. We just have to do control swap test in this two-particle case, which is the S2 group. And then as a result, you can show that if you just do local gates, after the symmetry adaptive transformation, you can show that you can produce a superposition of singlet state and triplet state. And then you can do downstream sort of dynamics evolutions. And then here's some real quantum computer run without error mitigation. There's a reasonably good agreement. And this is like a phase estimation that you can combine together. Now you can do 4 sectors for the H2, which is singlet, fermionic, or triplet bosonic, and all that together in one go. And there's also the power statistics that you can show if you actually work with a larger non-abelian group, that you can deal with some anion sort of statistics. So I will skip this and then just mention some future directions. For example, if you actually really get serious, right, you can do a full-blown simulation of molecules with electrons, and nuclei, and rotations, and all that symmetry all coupled together. And as you know, there's lots of interesting coupling channels between these different degrees of freedom in quantum chemistry that often plays a very important role. So this framework will allow you to do that relatively efficiently. And so there are many open questions, especially for this continuous group case, that has very interesting applications beyond the simulation, actually, also in error correction and even in some classical simulation of rigid bodies. And then we hear a lot of talk about analog devices. So one of the natural questions is, will continuous variable quantum resources or analog devices help us better realize this continuous group symmetry transforms than a qubit version? So here's the takeaway. I wanted to thank the collaborators, especially Victor Bastidas and from NTT Research and Nathan Fitzpatrick from Continuum, who are the co-first author of this paper. And then you can check the paper link, I think, there. And then we'll stop here, and then thank you for your attention.